Hi, I'm Sam Folkart and I'm going to demonstrate my WebGL program for visualizing the time varying temperature distribution across a rod. So the tools and libraries that I used were fundamentally this WebGL fundamentals libraries and guides. So they were written by Greg Travers, and I used the WebGL utils for setting the buffers, setting the attributes, setting the uniforms, setting the shaders, and I use the m4.js for like look at, perspective transformations, and then just translate, scale, rotate, things like that. And so everything in this program was done using HTML, CSS, and JavaScript. So the WebGL is run inside a canvas object in HTML. And then just like any other HTML object, you can have event listeners, you can have mouse over, on click, resize. You can use anything, any normal JavaScript that you can with a website. And so this is an example for the HTML. The program that I used to make this PowerPoint, I could not figure out how to put tabs in it, so sorry for that. But we first make a div to put the WebGL inside, then we put the canvas. And the canvas exists in, or the WebGL exists inside the canvas. We The canvas has a WebGL context that we can get and we can activate. And then the div there for the heat controller and the controller item is just buttons for selecting the number of Fourier series coefficients. And we can attach the WebGL context to the canvas by just using the normal HTML DOM, doing the get element by ID, and then saying GL equals canvas.getContext WebGL. And then once you do that, WebGL is exactly the same as C++, OpenGL. You can do GL bind buffer, you can do GL uniform, you can set all the uniforms the same, everything like that. And then you can do GL draw arrays. You can specify your primitives with GL triangles, GL line strip, GL triangle strip, triangle fan. Everything just has the GL dot in front of it. And so everything's the same as C++. And now that we know about WebGL, we can start talking about the program and solving the heat equation. So the heat equation is a surface plot. When we have the one-dimensional rod, the x direction is the rod's length, and t is the time after a certain amount. So, you kind of just have an initial distribution, and then you let it run. And so the surface plot is actually a Fourier series. It's this cosine times an exponential decay. And the way you calculate the Fourier series coefficients is just like any Fourier series. And these are the formulas down there. So in our code, we approximate these series as finite summations. And here's where we do this. This function calculate Fourier series coefficients. We first make an array to store all the coefficients, and then the A naught is just the average. So we just sum up all of the points in the initial distribution, and then we just push the average divided by the length, which is just what an average is, into the coefficients. So that's how you get the first component. Then the next components are your normal Fourier series stuff. So we add up the cosine n pi x over a times the function. So that's where we do that. We do 4n equals 1, n is less than the number of coefficients, and then we have a for loop for every point along the distribution. And so we multiply the cosine times the initial distribution, we add it up into the sum, and then we push that into the coefficients. Then we do another iteration of the loop, then we do another iteration of the loop. We keep doing that. And so now that we have the coefficients, we can calculate the mesh. And so in OpenGL, when you're doing a mesh, you need each vertex of the triangle to be specified. So you normally need 3 triangles straight up in a row. And we don't want that because we want to keep reusing the mesh. And so, or also, first we just have a mesh. So first we even need to get the triangles, the tips of each triangle. And so something like Delaney triangulation was too complicated. The cosines are non-convex. There's a typo there that says highly convex, but it's the opposite. It's highly non-convex. And because they're evenly spaced, they're square spaced, we can just take the initial vertex in the bottom left corner, we can move to the upper right one, then we can say that's the next vertex. And then we can just move to the right end of the triangle, say that's the next vertex. Then we just repeat this, repeat this, repeat this. You know, bottom left, upper right, bottom right. Bottom left, upper right, bottom right. And so here's where we do this. We just take the indices of those and we put them into an array because we can use that for GL draw elements. Which is one of the things I found out doing this project is that you can just make an array called indices, and then you can just push, you know, the bottom left corner, the upper right corner, the lower right corner, and you can just repeat that for these inside of these 2 loops. And then once you do this, the whole thing is triangulated. You do get little errors like maybe one side of the mesh will only be triangulated, and then you'll have a transparent part. So in the actual code, this is run 4 times to get 4 sets of triangles, but this is the whole premise of it. And so once we have the mesh and we're rendering it, now we need to shade it. And so to have the heat map, we linear interpolate between red, green, and blue. And so since we do this linear interpolation twice, we actually have a quadratic interpolation, a quadratic spline. And it's a Bezier spline with a control point, but just one control point. So it's not a cubic spline. And so we have 3 vectors. We have a hot, a cold, and a medium vector. And then we linearly interpolate between the left 2 vectors. We linear interpolate between the right 2 vectors. And then we linearly interpolate between those 2 intermediate vectors. And then that's how we get the color, the height map. And here's where we do this. I have this function, quadratic interpolation, and this is inside of the mesh shader. So inside the mesh shader, we have this function. It takes a left point, it takes a right point, and it uses this mix function, which is built into GLSL. It's part of the GLSL specification, and mix does a linear interpolation between the first vector, the second vector, and then the amount that you want. So we just quadratically interpolate between this hot, cold, and medium vector, and then that's how we get the heat map effect. And that's everything that's in the program. So now I'm going to talk about future enhancements, and future enhancements could be shading. So originally I had implemented shading with a light source, and this did not work because the normals were wrong. The normals were incorrect. And there were errors, there were all kinds of things like that.